morning all, my name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about fast wavelet transform in color image processing. So, fast wavelet transform highlights the benefit of a faster compression and faster processing as compared to discrete wavelet transform with higher compression ratios at the same time and reasonably good image quality. In 1988, Mallet produced a fast wavelet decomposition and reconstruction algorithm. The Mallet algorithm for discrete wavelet transform is, in fact, a classical scheme in the signal processing community known as a two-channel subband coder using conjugate quadrature filter or quadrature mirror filters are there. So, when I going to the fast wavelet transform, so this fast wavelet is using for transformation of images from one form to another form. This fast wavelet transform highlights the benefit of a faster compression and faster processing as compared to discrete wavelet transform with higher compression ratios. At the same time, reasonably good image quality. In 1988, Mallet is produced this technique, that is a fast wavelet transform to decomposition and reconstruction of algorithm. The Mallet algorithm for discrete wavelet transform is in fact classical scheme in the signal processing community known as a two-channel subband coder using conjugate quadrature filters or quadrature mirror filters are there. The decomposition algorithm starts with signal S, next calculates the coordinates of A1 and D1 and those A2 and D2 and so on. The reconstruction algorithm called the inverse discrete wavelet transform starts from the coordinates of AJ and DJ, next calculates with the coordinates of AJ-1 and DJ-1, AJ-2 and so on. So, what are the coordinates are there? If any of the image, we have to take the two coordinates are there, x comma y. So, that x comma y I am taking as a f of x comma y. So, we have the discrete wavelet transform, Fourier transform, fast Fourier transform and fast wavelet transform. So, these are the different techniques applying for the images. So, the decomposition algorithm with the signal S next calculates the coordinates of A1, D1. I am taking as a, instead of x, I am taking as a coordinates as A1, D1, A2, D2, so on, AJ, DJ, AJ-1, DJ-1, AJ-2, DJ-2. So, like this, these compositions are calculating as a coordinates of the images with the inverse discrete wavelet transform IDWT. To starting with AJ and DJ, next calculates the coordinates are AJ-1, DJ-1, so on. Here, one example of fast wavelet transform. X of n I am taking as an input and finally it is the output. In between the input output, what are the stages are there? I am taking as a g of n and h of n are the two difference are there. The two we are taking as a, we are increasing the value of 2 here, decreasing the value of 2 here. Another is dividing as a g of n and h of n. Here decreasing 2 and decreasing 2. Here g of n and h of n. Here level 3. How many levels are there? It is a level 1, level 2 and level 3 are there. So, 3 levels are performed in fast wavelet transform. So, these are the x of n, g of n and h of n are the fast wavelet transformation techniques in the different levels to performing the transformation process, and level 3 is the final coefficients are there. Here, the filters are used to calculate discrete wavelet transform and inverse discrete wavelet transform. The orthogonal wavelet in the multi-resolution framework, we start with the scaling function phi and the wavelet function psi. One of the fundamental relation is the twin scale relation, dilation equation or refinement equation. Okay, so it is the equation 1 by 2 psi of x by 2 equal to summation of nz wn of psi of x minus n. So the filters are used to calculate the discrete wavelet transform. So discrete wavelet transform and inverse discrete wavelet transforms are the orthogonal wavelets for the multi-resolution framework. We start with the scaling function phi and the wavelet function is psi. One of the fundamental relation is the twin scale relation of dilation equation to the refinement of equation is this one. Okay, it is the equation for calculating the discrete wavelet transform and inverse discrete wavelet transform. And all the filters are used in discrete and inverse discrete wavelet transform initially related to the sequence of W. Clearly, psi is compactly supported. The sequence Wn is the finite and can be viewed as a filter. The filter W, which is calculated as a scaling filter, normalized is finite impulse response FIR of length 2n of sum equal to 1 and normally 1 by root 2. Okay, so DWT and inverse discrete wavelet transforms. The psi is the compactly supported sequence Wn and the finite can be viewed as a filter W, which is called as a scaling factor, and the normalized filter FIR filter, finite impulse filter FIR with length 2n, sum equal to 1 and normalization is 1 by root 2 and the normalization equal to 1. Okay, it is the operation of discrete and inverse discrete wavelet transforms initially. So wavelet analysis, which is the successor for the Fourier analysis, is based on the idea that the same information, the same signal can be represented in different forms depending on the purpose. To translate a signal into another form, a basis is first chosen, a set of linearity independent functions, and the signal is represented as a sum of these functions with some coefficients. The Fourier analysis, the basis consists of periodic harmonic function, a sine and cos corresponding the oscillations with a certain frequency throughout the domain of definition. So the wavelet transform, nothing but wavelet analysis, is a successor of the Fourier analysis based on the idea that the same information, the same signal can be represented in different forms depending on the purpose. To translate a signal into another form, a base is first chosen, a set of linearity independent functions, and the another signal is represented as a sum of these functions with some coefficients. The Fourier analysis of the basis consists of periodic harmonic function, sine, and cos corresponding to oscillations with a certain frequency throughout the domain of definition. Thus, having obtained the Fourier transform of a signal, we can determine its frequency spectrum and see which oscillations it consists of, or the signal characteristics of changing the example in time for sound signals or in space for images. Then we can decompose it into components by using wavelet analysis, in which the basis consists of shifts and scales of a certain mother wavelet function. In such representation of signal, we can track changes in the frequency spectrum, well as study the local structure of the signal at a certain frequency, at a certain scaling function. So, when we are going to the Fourier transform, so when we are applying the Fourier transform to the signal, we have to go for the frequency spectrum. We know that what is a frequency spectrum, the set of frequency ranges that is called a frequency spectrum, and the signal characteristics are changed time for sound signals or in space for images. Then we can decompose it into components by using wavelet analysis, in which the basis consists of shifts and scales of a certain mother wavelet function. And the representation of signal, we can track changes in the frequency spectrum as well as study the local structure of the signal at a certain frequency at a certain scale. The representation of data in the form of wavelet coefficients is usually more compact than the original representation. From the perspective of the information theory, such a representation has less entropy. Moreover, such a representation also allows to obtain an approximation of the original signal with a given accuracy by using only a fraction of wavelet coefficients. So, when we are going for the wavelet transform, what are the wavelet coefficients? These wavelet coefficients are usually more compact than the original representation. The perspective of the information theory, such representation has less entropy, and these representations are allows to obtain an approximation of the original signal with a given accuracy by using only a fraction of the wavelet coefficients. Here, 2D discrete wavelet transform is actively used in image compression in popular formats JPEG 2000 and DJB. Due to the ability of transition to multi-scale representation of data, it is also used in image enhancement algorithm such as noise reduction, filtering, fast scaling, and in artificial intelligence to reduction of filtering, fast scaling, and artificial intelligence. The applications as feature extraction and segmentation in compressing the sensing applications during the signal reconstruction. So, when I am going for the 2D discrete wavelet transform, the it is using also in image compression, etc. And the ability of transition to multi-scale representation of data are also used in image enhancement algorithm such as noise reduction, filtering, fast scaling, artificial intelligence, and of the applications of feature extraction and segmentation in compressing sensing applications during signal reconstruction. The discrete wavelet transform of a signal is obtained by sequential applying of two filters, low pass filter and high pass filter, with decimation to elimination redundancy. Such an algorithm is called the mallet algorithm and can be used both for decomposition and for reconstruction. As a result, a signal is decomposed into two components of approximation, lower resolution and details. By applying this decomposition repeatedly to low frequency coefficients, a multi-scale decomposition is obtained. This allows to obtain or adjust information on a wider frequency spectrum. So when I'm going for the discrete wavelet transform, these are the low pass filters. Another one is a high pass filter. These two filters are using here with the decimation of elimination redundancy. The mallet algorithm can be used for both decomposition and for reconstruction. Decomposition and reconstruction. As a result, the signal decomposition into two components, lower resolution and higher resolution. The decomposition repeatedly low frequencies, coefficients, and multi-scale decomposition. Decomposition. This allows to obtain the information of wider frequency spectrum. Since the images are two-dimensional, their discrete wavelet transform is performed both vertically and horizontally. The result is four fragments, that is called subbands, with half the width and half the height, one of which is a smaller copy of the image, LL subband, and their remaining subbands contain the information about the horizontal and vertical and diagonal. At each subsequent step of decomposition, the subband is replaced by four smaller bands and the total number of subbands increases by 3. The algorithms are used to construct the signal of higher dimensions of video sequences in 3D signals. So, when we are going for the 2D discrete wavelet transform is performed vertically, horizontally, and diagonally. So, when we are going for the horizontal, vertical, and diagonal, these are the four subbands are there. These subbands are half the width and half the height. Half the width and half the height. It is height and it is a width. So, LL subband, HL, LH, HH. How many are there? Total 4 subbands are there. These 4 subbands belongs to vertical, horizontal, and diagonal. Each subsequent step decomposition with LL subband is replaced by 4 smaller bands. The total number of subbands increases by these 3. The algorithms are constructed for signals of higher dimension. The video sequencing is a 3D signal. Here, the original image, that is the input image, it is a discrete wavelet transform is applied to the transformation process, and it is a subband of 2D wavelet coefficients after first and second discrete wavelet transform of the image. So already in the previous we discussed LL, LH, HL, HH. How many are there? Total 4 subbands. Total 4 subbands are there. So we are taking as a discrete wavelet transform is applied to one image, input image 1, and it is the input image 2. So first image I am taking as a LL1, HL1, LH1, HH1. Another one is a LH2. Actually, it is a LL2, HL2, LH2, HH2, like this actually. But here what is happening? In this first quadrant, it is a 4 are there. First 3, 1, 4, 1, 2, 3, 4 subbands are there. So in this first subband, another is occupied, that is the LL2, HL2, LH2, HH2. So in the discrete waveform, another discrete waveform, another is occupied, this one. That is the first and second discrete wavelet of the image. So in this LL1, 4 subbands are there, LL2, HL2, LH2, HH2. So here 4 subbands, here 4, 8 subbands are there, first and second discrete wavelet transform of the image with the comparing with the original image of the 2D wavelet coefficient. These are the references. So now up to now we discussed fast wavelet transform, including with the discrete wavelet transform and inverse discrete wavelet transform is presented by Mallet. It produced in 1988 with the discrete wavelet transform. Classified the signal processing community, 2-channel subband coda, conjugating the quadrature filters, and it is a decomposition of algorithms. Next calculates the coordinates of A1, D1, A2, D2, AJ, DJ, AJ-1, DJ-1, AJ-2, DJ-2, so on. It is the 3 level of coefficients of fast wavelet transform, and it is the filters used to calculating the discrete wavelet transform and inverse discrete wavelet transform using with phi and psi symbols are there. Here it is the equation, and it is the wavelet analysis for the Fourier analysis for same information about the signal can be represented in different forms of depending on the purposes. To translate a signal into another form, the basis of first chosen a set of linearly independent functions. The signal is represented as these functions with some coefficients. And the basic analysis is the basis consists of periodic harmonic function with sine and cos corresponding of oscillations with a certain frequency throughout the domain of diffusions. The signal characteristics are changing with the time slots, with the sound signal and space of the images. We can decompose into a components by using wavelets, which is the basic concept of shifts and scales of certain wavelet functions. Such representations of the signal, we can track the changes in the frequency spectrum, well as study the local structure of the signal and a certain frequency of the scales. The representation of the data with form of wavelet coefficients is usually more compact with other original representations. To form the respective information theory, such representations has less entropy. The representations allows to obtain an approximation of the original image with accuracy and wavelet coefficients. The 2D discrete wavelet transform is transformation technique for image compression, like JPG 2000, we are compressing the image without losing any of the data with the multi-scale representation data. Image enhancement algorithms are used to noise reduction, filtering, and fast scaling with artificial intelligence applications. The extraction of the segment in compressed sensing applications during the signal reconstruction. The discrete wavelet transform of a signal is obtained by sequential applying of two filters. So it is a discrete wavelet transform of low pass filter and high pass filter with low frequency components of multi-scale decomposition. It is a mallet algorithm for the decomposition of the reconstruction. And the lower resolution version is detailed of low frequencies, and the multi-resolution is obtained to allow us to obtain the information wider frequency spectrum. So it is a image segmentation of two-dimensional with a discrete wavelet transform is performed both vertically and horizontally. So when I am taking the vertical, horizontal and diagonal with 4 subbands, LL, lower, lower, higher, lower, lower, higher, higher, higher. 4 subbands are using in this diagram. It is the subbands of 2D wavelet coefficients after the first and the second discrete wavelet transform of the image. It is the original image with the discrete wavelet transform of this one. Another discrete wavelet transform is this one. Okay. So 2 stages of first and second stages of discrete wavelet transform of the image. Okay. It is about the fast wavelet transform, discrete wavelet transform, and fast Fourier transform. So it is the equation for discrete and inverse discrete wavelet transform with phi and psi are the functions of these transformation functions, and we are using finite impulse response FIR with the length 2 with sum equal to 1, normalization equal to 1 by root 2, and the normalization equal to 1 here using within discrete and wavelet transforms are there. It is a 2 stage of 3 level and 2 stage of coefficient of image segmentation of fast wavelet transform. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.